Okay, so I think we can get started right now. Letting the last people come in here. Great. So, thank you for joining. Hope you had a great KubeCon so far and Cloud Native Con so far. And hopefully you also had like a great party yesterday. Yeah. If you had a great party yesterday, probably you feel like you failed today in the morning with a little bit of hangover, but that's all good things. So, welcome to my talk. What happens when containers fail, or like the mushroom cloud effect, what happens when containers fail. So hopefully it works. So my name is Alois Mayr. As you might already have recognized, I have a very German accent, but I'm not from Germany, I'm from Austria. Like, you know, the small little country in the center of Europe. And whenever I give a talk in the US, Austria is some kind of, yeah, it's a small little country. I mean, we have the size, I think the Austrian population is about the same population as Manhattan. So, but it's at least larger. But whenever I talk to people in the US, they always connect Austria with the sound of music. And that's weird for us, because in Austria, no one knows about that. I don't know why. No one in Austria knows about the sound of music. So that's why I've never seen the sound of music, but seems to be a pretty funny thing. So like we have a very nice landscape there, like huge mountains and all that cool stuff. But yeah, let's talk more about myself. Yeah, I've never seen Sound of Music, but I've often seen much more like modern technology stuff and stuff like that. And you maybe know this guy. Yeah, it was the governor. And yeah, but since I've joined Dynatrace, I have, seen much more technology stuff and new technology stuff. And basically, I'm one of the guys in the innovation lab of Dynatrace who, deal with like new technology, trying to bring monitoring to cloud providers, to cloud platforms and stuff. And for me, it's like all that is related to cloud containers, platforms like Cloud Foundry, etc. So some words about Dynatrace. Whenever I give a talk about something from Dynatrace, most of the people don't really connect Dynatrace with like modern cloud platforms. Dynatrace basically is around since 2005. It was founded in Austria and is now headquartered in Boston. Yeah, we have around 1,600, 1,700 employees worldwide, and about, let's say, 400, 500 engineers. Most of them are in Austria and Poland. So most of the engineering happens in Europe. And we have 8,000 customers across all industries. So like financial industry, like insurance companies, banks, manufacturing industry, all that things. And over the time, over the last decade, we have seen lots of different problems in their stacks. So when you go back in 2005 and you provide monitoring for like a bank, you do not deal with like modern stuff these days, like VMware. You dealt with like mainframes. Yeah, you needed to deal with huge Java stores or Java or .NET applications and monoliths. But nowadays, we need to deal with like more modern things like highly dynamic environments, Docker environments, Kubernetes environments, where everything comes and goes pretty frequently. A container can live for seconds only, but you also need to be able to deal with like this highly dynamic infrastructure. And yeah, we can do that. But now I spend some words about myself and about Dynatrace, so how about you? I guess most of you have already dealt with running containers somehow managing containers somehow. I mean, we are at KubeCon here. Most likely you have done that with Kubernetes. Despite that, I want to do a show of hands. So I hope every one of you has somehow dealt with containers at this time. Who of you deal with containers? Yeah, almost all. That's good. And the next question is, whose life has become easier since like there are containers out there, so since there's Kubernetes out there or something like that? It has become easier compared to like the monolithic. Yeah, that's true. That's good. And who of you feels more like a dev, and who of you feels more like an ops guy? That would be interesting. Usually at this question, the dev guys, all the dev guys say, okay, it has become easier because it's really easy to package everything into a single image and let the ops guy care about the rest. And for the ops guy, it should be supposed to be easier because he can just run the container with the image, right? But for most of the ops, it became not really easier because they have to deal with an additional layer of complexity. There's an additional layer of, you need to take care of different versions of your container runtime. You need to take care about the orchestration layer. You need to deal with software-defined networks. So you have a lot of new complexity coming in. That's why it's not really easier for ops guys to run containers. Yeah, what's needed to make it easier? Yeah, I think we can skip this question since we are at KubeCon here. So, as I've already mentioned in the introduction, we have a lot of experience of our customers where we have seen what can go wrong in all different kinds of environments, like in huge monolithic applications, for example, e-commerce stores. What can go wrong when you need to deal with SAP? What can go wrong if you want to run a huge data processing cluster? So lots of different stories in here. And over the last 2 years, we also learned a lot of things of running containers in production. And usually I do always like this. We can talk a lot about containers. And this time I want to talk about the mushroom cloud effect. And yeah, I think most of you would immediately know what I mean with the mushroom cloud effect. But probably sometimes people are in there that not really get the first place what the mushroom cloud effect is all about. So TLDR, hopefully you can see that. That's bad. So this is the mushroom cloud effect. So this should have the same shape as a mushroom, right? And what you can see here is a real-time is a screenshot of a real-time dependency graph of all components within an environment, within a container environment that has failed during an issue. And all the components, how the components have been connected to each other with all the dependencies in there. So it looks like a mushroom because there are lots of components in there. So let's put some layers on, over this mushroom. So at the bottom here, we see, okay, here are lots of, let's say, Docker hosts, like lots of Linux machines running a Docker engine. And yeah, so this is probably the root cause of many problems here. Yeah, there are all the hosts running actually application containers. At the second level, there are all the processes in containers. I mean, containers are just like isolated processes. That's why we treat processes and containerized processes the same way. So to say that there are lots of containers there and all the processes. And at the top of this layered picture, there are all the applications and services. So usually when you deploy a microservice, for example, you will package everything into a Docker image, run it somehow on any host, and the microservice is being offered by the container. For example, in this case, PHP service, Java service, JavaScript, or whatever. And within this graph here, we see all the connections and all the relations. We don't really see them because since there's too many, but you could, zoom into there, and you would see all the connections between all those components. And that's why this talk is named the mushroom cloud effect. Because being able to understand the real-time behavior of a container environment is very important to know where is the root cause if something goes wrong, right? Okay, before we go into a post-mortem analytics of this mushroom here, I want just to spend some words about how people build a system nowadays. Usually, you know all the stories, all the successful stories of Netflix and all the famous examples out there. You have lots of services or microservices. All the services are somehow connected to each other. They need to communicate with each other. You also have dependencies between services. So if you have service A talking to a service B, you have a dependency between those two services. But it's not only on the service level, but also like on a versioned service. So if you have like a service A in version 1 and version 2, the version 2 might have other dependencies than the version 1 of the same service. So you have really like a very complex graph of all dependencies within your entire environment. And you always most likely have like a requirement of 0 downtime. When you build such a system, you usually build it that it's available all the time, and you don't want to have downtime when you upgrade anything. And this brings me like to our yesterday's closing keynote from Brandon Phillips, who just demoed us how easy it is to just upgrade a Kubernetes cluster to a new version with one button, right? Yeah, and there are some other platform-related aspects as well. So it's not only having like lots of services you need to offer to your customers, you also have like platform aspects. Like most often those services are like container-based, and those services usually are clustered. For example, if you want to deploy a service, you will most likely run it like multiple times, like in 5 containers, like building a replica set with 5 instances so that you run 5 containers for the same service. And all of the containers are ephemeral, and the underlying infrastructure, in this case Kubernetes for example, will take care of whether your services are still up and running or not. And if the orchestration layer detects that there's something wrong, it just kills the container and starts a new one. Always trying to have a decent amount of containers running for a service which was defined by the operator, or probably you do also auto-scaling. So in this case, you will see on the left-hand side, we have like one service. It's called the booking service. And the booking service basically is made available through 6 different containers. And one container out of these 6 disappeared. It was offline for any reason. And right now, it's like provided by 5 different containers. As already mentioned, we don't really differentiate between processes and containers because, processes in containers are just isolated, that's it. And those 5 processes or containers actually run on 5 different hosts. And in this case, in 2 different data centers, meaning in 2 different availability zones on AWS. And what we also observe is, here is like the one container that is offline right now. What we also observe is that deployments are no longer static. So this is like the new challenge of all the operators in order to figure out what is the optimum amount of containers running for a specific service, for a specific microservice. Because you don't want to waste the resources. You want to save resources to make it easier to schedule other tasks or whatever, and save money on renting AWS resources, for example. So what we also see is that in this case, in the morning, we have low load for a specific service. That's why 2 containers are enough to run or to serve a specific service. During noon, there is like a high traffic, a peak load scenario where we scale up to, I don't know, 7 containers. And in the afternoon, the load goes down, so that's why for customers, it's enough to also, again, kill some of those containers and save resources, right? And this perfectly fits, basically, to the story out there from Supergiant, I guess? Yeah, so the guys out there that also try to, like, save resources on extending and shrinking clusters. Okay, how does a microservice environment with lots of services look like in practice? It looks somehow like this. So in this case, we have just taken the booking service here. There's a single service, which is called booking service, basically, in version 5. And this is just one service out of 1,000 services in this cluster. And what we see is here on the left-hand side is that the deployment complexity of this service. We see, okay, this single service is being deployed through 5 different containers on 5 different machines on 2 data centers. But on the right-hand side, we see all the communication parts between of this single service. So like this single service is talking to all those blue-colored bubbles on the right-hand side. And yeah, it's kind of a mess there because lots of services in there, and it should visualize you how complex such an environment could be. So it's not only just, we see the containers and that's it. What really helps you is in figuring out how these services really connect to each other and how they relate to each other. This brings me to the next slide, which is when you have a microservice environment, it's really all about service dependencies. So you really need to figure out which services are talking to each other. So I don't know who of you have attended the keynote yesterday evening. There was a short track about, a short session about open tracing, which basically tried to solve the same problem, right? They want to figure out when a request comes in through a gateway, comes to like a microservice, is forwarded to another service, then to a database somehow, and then goes back again to the browser or wherever. And what we do here is basically the same without requiring you to add implementations, libraries to your code. But we do it like a little bit differently. But what you can see here is, the resolution isn't really good. So requests coming in through this service are like spread across these 3 different services, and you will see like how the request goes through your entire backend. And imagine if this is again the booking service, the starting service, each of those services most likely is deployed again multiple times with, let's say, 5 containers, are on different machines. So they have the complexity is pretty high. So what actually happens when containers fail? So what happens when this single container fails here? Yeah. So usually the answer is it depends. The platform is built for resiliency, so that's why the platform takes care of just starting a new container of the same image, and everything is good, right? So usually, if a single container fails, most likely it's not a problem. But what happens if another container fails? Like if 2 or 3 containers of the same service fail, or if a failing container has an impact to a container of a completely different service, for a completely different Docker image, what happens? It really depends. And that's why it's important to know how these containers relate to each other and how the services relate to each other, right? So in this case, a single failing container do not have any problem or do not have any impact on other services. Okay, so what we have learned is basically, cascading failures obviously lead to issues and might lead to the mushroom cloud effect, where you have like a snowball effect. So if a container fails and it's an important container, it most likely destroys other containers, and it's like a snowball effect then. Yeah? And now I want to walk through one example we have observed where a single container really caused a little outage. And this again is some kind of a mushroom cloud. You know, it's basically the same visualization as before, but with less components included. So in this time, we see that there was an outage or there was a problem, and all those components affected. We can see here at the bottom that there basically were two Linux machines, and at the top there was a couple of services like Tomcat services, an Apache web service, Nginx. There are some databases in there, so lots of different components and how they relate to each other. And now I just want to walk through step by step what happened at this issue. So what was the problem? So we have seen that this problem at a customer where the customer had a real huge pain. So they used to have like a huge monolithic system, and they had an outage in their monolithic system, and they were not able to figure out the root cause of the outage. They were not able to find a solution for the outage fast enough, so they lost a lot of money during the outage. That's why they decided they want to get rid of the monolithic application and migrate to like a microservice application. And what they did was they pretty nicely sliced down the monolithic application into a microservice environment, and they used Docker for just running the microservices, because it was, I think, back in 2014 or so, or 15, a pretty nice way on how to do that. And the only problem was that containers were pretty new to them. And they were really, angry that probably the microservice environment could also fail, right? So what they did, they didn't really trust containers. That's why they decided they wanted to have access to the log files anytime. That's why they decided that they will just, mount a logs partition on every host within every container running on the host, so that every container on a host shares the same log partition of the underlying host. Okay? So this was like a design decision of the operators, just to make sure that if a container fails, if something goes wrong, that they will have access to their log files stored on the partition. So that was the reason why they wanted to have like a shared logs partition. And they had no log rotation or stuff like that in place, and no proper log management. But what happened? At a certain point in time, the logs partition ran out of space. If you have like a logs partition and all containers writing the application logs into the same logs partition, I mean, it's just a matter of seconds, minutes, hours, I don't know. And at a certain point in time, the logs partition ran out of space. So this was basically the start of the hell. So how the problem basically evolved over time. So the orchestration layer they used had some health checks for every container. And the container were not able to write logs anymore. That's why the health check failed. So what was the job of the orchestration layer then? It just killed the container, because it's not healthy again. Just kill the container and start a new container, because that's the job of the orchestration layer. So everything is fine, right? Okay, but there was still no free space on the logs partition. So actually, the problem wasn't solved. It was just like a new container trying to write again on the same logs partition. So what happened next? Yeah, I mean, yeah, the orchestration layer again detected that the health check failed, just killed the container again and started a new one. So it was like kind of an infinite loop of killing and starting containers due to like failing health checks all the time because like the log partition was full. I mean, it wasn't really infinite. So actually, it just took a couple of minutes, I guess. Then happened this. So the next partition ran out of space. So varlib docker, in varlib docker, it was like the default configuration at that time, where Docker, stores like the container file system. So with every container you start, you need a specific space in order to have like a space available for the container file system. And if you kill the container, the old file system of the container will not be removed. So that's why after some minutes or so, the varlib docker directory ran out of space as well. So there was one more problem in there. So we have a full logs partition, a full varlib docker partition. The real problem was that varlib docker was on the root partition. So basically the whole Linux machine was dead, which lead to cluster nodes. So this single cluster node, or after a while, multiple cluster nodes were no longer available to run containers. And that's a bad situation if you have a cluster just for running application containers and you can't run any containers anymore because of that problem. So how this problem has affected other services? It's just like containers that do not run, but you always run containers by purpose. In this case, there were multiple services affected at the top of the graph. I mean, if the resolution would be better, then you would see like Tomcats, Nginx, and all that things. And we also observed an increased failure rate, which basically means that other services tried to connect to or consume these services and just got a timeout or whatever, right? So we detected increased failure rates here. So the problem, how the problem could have been avoided? Yeah, it's pretty obvious. Don't do that stupid things of sharing logs partition. Use log drivers. Remove containers if you don't need them anymore. So just remove containers if they're ext 10 or 20 or whatever. And move your varlib docker partition, or move like your partition where you store like container file systems to another partition than the root partition. It's I think a good idea in this case. So, but this is not really specific to a container environment. I mean, this can happen in all traditional systems as well, right? But it was really a problem in this environment because the people there, the customer, were really surprised that this could happen in new technologies as well. So what did they do? So when they have learned that this specific case wasn't a good idea, they wanted to be prepared for Black Friday. And they don't want it to run into the same problem again during like their best time in the year where they sell the most products. So that's why they tried to break the cluster early, which included everything. They really did like massive load testing, and they included everything. Everything means they produced lots of traffic to the services, to the Tomcat services, to the microservices. They also played around with all the containers. They just killed containers and tried to figure out whether orchestration layer is able to detect that and start new ones. And they also did all the monkey stuff with EC2 instances. They just killed EC2 instances and got rid of simple or of specific nodes in the cluster, right? And they tried to figure out whether they can survive 3 days of massive load on their system. So after the 3 days, during their load test, more than 13,000 containers were included, and about 3,400 services have been tested during the 3 days. And this is like, again, the mushroom cloud, which I have shown you initially at the beginning, where we basically analyzed 820 billion dependencies between all those containers, services, processes, and hosts. And only like two Docker hosts really had some TCP issues, basically TCP issues. TCP connectivity issues basically means they were offline. Yeah. So this was one story we have seen at a customer. The customer didn't ask us whether they can run load tests against their cluster, but we were able to capture that afterwards. So what is the point here? If you run a huge cluster with lots of services with different versions, run the versions of the services in multiple containers. When you leverage Kubernetes, you can do rollbacks and stuff, you know. Then it's really important to know all the dependencies. Otherwise, you won't be able to figure out whether something goes wrong or not, right? And what we have learned is it's really important to have an automated approach in order to figure out the root cause of a problem, right? By analyzing all those dependencies. When we figure out, okay, when a process dies because the container was killed, what is the effect of the killed container to a service? What is the effect to another service this service is using, right? So this is really important to figure out what is actually the root cause of a problem. Okay, I think it was too fast. How do you deal with large container environments? Do you run any large container environment? The question is, what is large? It always depends. I mean, we have seen yesterday tests where they run like thousands of Kubernetes nodes. That would be large. Okay, we have a free trial. Feel free to test it, and I would be happy to get some feedback on what we do. Are you interested in a demo? Okay. So I think we have, 5 minutes left or so. Yeah. Can you read that? Okay. So this is like the dashboard of our demo environment. The demo environment isn't really, it's like a traditional environment running multiple things there. And this is like one screen you have seen before. Let's pick some of those guys, where we see, okay, in this case we run, I think we need to click 10. Let's pick this guy, or not. Where we see, how the services are related to each other and how they are deployed on machines. As you can see, there is a Windows machine. So we have agents that run on Linux and Windows, so you don't really need to use Linux only. And I want to go back. Let's see what we see on the service level here. Authentication service. Oh no. Let's take this guy. So what we have is our agents inject into Docker containers and are able to see what's going on within your applications. In this case, we see, okay, we have one application, which is a web application. It's VMware easytravel.com, which basically sends requests to our front end in the back end. And this front end has calls to other services like an authentication service, booking service, and we just can let you show here, okay, this service is like here deployed, only one process, and talks to other services there. But we can also jump into a service flow, which basically shows you how this single service, how the requests through this service traverse through the system and end up somewhere in, for example, in a MongoDB. So in the MongoDB, we see, okay, what are the queries to the MongoDB and how long they took. Let's look at aggregations here. So we have 505 queries there, and the average time is 14 milliseconds. But we can also check, okay, who actually is calling this MongoDB and figure out, like, backwards, so what are the services querying my database, right? To go back to the service level again. Oh, don't have much. Okay, but that's one point, and the other point is we also see, okay, how much time is spent in code execution, in service execution for microservices. So if you want to optimize your microservice infrastructure, you're most likely also interested in increasing the performance of individual services, right? Let's go back to this guy. So as I've mentioned at the very beginning, we know all the dependencies. When we deploy our agent, we discover all the dependencies within your entire environment, like all the hosts, processes, running in a container or not, we don't really care. Everything that's going on within your container, within the processes, like for example in a JVM. And with all this information, we are able to figure out when something goes wrong, and we can pinpoint you to the root cause of a problem. So in this case, we see, okay, we have on the left-hand side 2 problems. Basically, two applications are impacted. So these are 2 websites which we have. And the root cause basically was, so the impact was a user action degradation, user action duration degradation, which basically means the response time was too high, right? For the easytravel B2B data website, and the slowdown was, crazy. But the root cause basically was that the check destination service in the back end caused the problem, right? Let's check this out. What we see here is, okay, during that period of time where we figured out that there's a problem in your environment, we see, okay, at this time here, the response time went up to 12 seconds. And let's just analyze the response time here. And we will see, okay, the code execution took like 4 seconds longer than it used to take in the comparison time frame before. And we even see, like, at the code level, what was the impact on the code level? So what was the problematic situation in the code level here? Let's go back. And the mushroom cloud I've shown you before, here in this specific problem, this also is like a kind of a mushroom cloud, where we again see like all the hosts at the bottom of the graph, and at the top of the graph, the applications and services. And we can even replay that, where we see, okay, how a specific problem, in this case, the problem with the check destination service in the back end, has evolved over time, right? Yeah, and see like all the events we have detected at specific components within the environment. Yeah, and yeah, the end of this problem replay, we see everything is green again because someone fixed the problem. Any questions?
How do you do, you sort of mentioned it briefly, but how do you instrument the application to be able to do all of this? What do you have to do there?
How we instrument, so the question was how we instrument the applications so that we are able to see like what's going on within the applications, all the queries to databases and all that stuff. So what we do is you just need to install an agent on the operating system. So let's go back. So here are all all our VMs or EC2 instances or whatever. You just need to place an agent on the machine, and whenever we detect that you start a new process, be it like a JVM, a Tomcat, a Node.js process, a Docker container running a Tomcat, we just inject the agent into the process. For instance, in Java, this basically means we adapt the JVM startup parameters and inject our agent into the JVM. So that's like the default way in how to monitor JVMs, right? And this way, we are able to monitor what's going on within the JVM, right? So we do their bytecode instrumentation. We see, okay, what's going on within the JVM, report all the data to our cluster, and in our backend, we can all correlate and analyze all the information coming from different parts in your environment, coming from the host itself, coming from the agents running in the processes in the JVM, but also when we detect that your service, for example, delivers HTML, right? We are also able to inject a specific JavaScript snippet, which allows us to track what the user is doing in the browser. So if the user hits a button in the browser, this was the example I've shown you before with like the impact to easy travel b2b.com, where we have detected that for the end user, it was a slowdown of like 2 minutes. We are able to detect that because we inject agents into HTML. So we can measure what's going on in the user browser, what's going on in the back end, with all the services, all the microservices, and correlate all this information and analyze it. And with all the dependencies, we are able to really figure out what is the root cause of a problem, right? So that's how we.
Do you have support for certain languages or certain?
Yes. Yes. Yes.
It's a follow-on question to that. You're describing running a 3-day stress test with sort of chaos monkey activity going
Yeah.
on. What precisely were you trying to analyze during that, and how does that relate? How do you use that information in the sort of service flow diagram for the root cause analysis?
Okay. So the question was how we analyzed all the information during the 3 days load test, right? So the 3 days load test wasn't done by us. It was a load test by the customer. The customer just wanted to test the infrastructure and had our monitoring solution enabled, right? We didn't really do anything there. We just were there, just monitored everything. But what we have detected was basically that some of the services had higher failure rates, had outages, because of 2 hosts had too much traffic that they weren't really able to deal with the traffic, right? So we didn't do anything. The customer decided to run the load tests. We just captured all the information and visualized them, and in our backend we just run our analytics.
So as soon as you've got your agents in there instrumenting it, that gives you enough information to construct.
Yeah. So everything you can see here is just like a visualization of all the monitoring information we get from the agents deployed on the cluster, right? Like everything on the host, processes. Let's take this guy. see if there's something interesting in there. Yeah, I mean, that's a boring one, yeah. Okay, so default metrics. So this guy is really bored, doesn't do anything. But we see like we would also have access to log files to enrich our information and to make sure that we can also give users, our customers, insights into log files during an outage, right? Any more questions there?
Looking at your technology support on your website, Golang isn't listed. Is there any support for Go microservices?
Right now, we have not a Go support. You know, Go is pretty, it's hard to monitor Go the automatic way. So we always strive for just placing an agent somewhere and monitor everything automatically. We don't want our customers to that they need to configure anything, you know, that it's hard for them. But Go definitely is on my wish list, at least. But for Go, it will be hard. Probably we can do something like an ADK or something like that. Yeah. But right now, Go is not supported. Okay. Okay, thanks.